In the previous section, we measured time between events using the tick count express VI. By the end of this module, you will be able to benchmark loop periods using the tick count express VI. If you want to benchmark your loop periods, you can use the tick count express VI to do that. So the way that you would use it is you're essentially using the tick count express VI to calculate the time difference between each iteration of the loop. So if we take a look at that block diagram down there, notice that there's a comment there, and just imagine that in this while loop there was some code that you want to benchmark. Okay, so let's say you have some code there. What you would do to benchmark the loop period is you would add that tick count code that you see at the bottom of the loop. So notice that we have a tick count express VI that's grabbing the current tick count, and then it's going to store that in the shift register. And then on the next iteration, it's going to take the old tick count and subtract it from the new one to get your loop period. The benchmarking code here executes in parallel, so it doesn't add any additional time to the loop period. Okay, and when you're done benchmarking that particular loop, what you can do is you can just remove that benchmarking code, and that way you'll save some space on your FPGA. So when you're benchmarking your loop periods, you want to make sure you watch out for rollover. So if the code that you're benchmarking is going to take more time than the maximum value the tick count can handle, then the elapsed time will end up being much lower than your expected value because of rollover. So when you're doing this, you want to make sure that you set the units, ticks, microseconds, or milliseconds, as appropriate, and also you want to make sure you set the size of your internal counter appropriately. So again, we see this table. Let's say you're trying to measure something and you're expecting that the loop period is going to be something around 35 milliseconds. Well, if millisecond resolution is good enough for you, then you can choose milliseconds to be your units, and because it's something less than 256 milliseconds, you can choose an 8-bit internal counter. But just be aware, if for some reason that loop period goes above 256 milliseconds, you're not going to get the expected result because of rollover. At this point, if you can, this would be a good time to do exercise 5.2, where you're going to use the techniques that we just talked about to benchmark a while loop period. So right now what I'm going to do is I'm going to open up the solution and walk through it with you. Okay, so let's take a look at this exercise. So right now we've got an FPGA VI thermocouple max and min benchmark right over here, and let's take a look at the block diagram. So the purpose here is we want to take some code and we want to benchmark it and see what the loop period of this while loop is going to be. So the code that we're trying to benchmark right now is we've got a FPGA I/O node, and we're reading a thermocouple 0 channel. We're taking that output out, and all these calculations here, what we're trying to do is we're trying to figure out what's the maximum that was reached, and what was the minimum that was reached. Okay, so just pretend that all this is some code inside the loop, and we want to benchmark the loop period for this loop. So what we do in this exercise is we add some code, and this code is already shown over here. Okay, so what we're going to do is we're going to add this tick count function, and we're also going to add a shift register. So what we're doing is we're taking the current tick count, we're subtracting it from the tick count of the previous iteration, and then that result is sent to our loop period. So our loop period is going to tell us the period, in this case in units of ticks. So if we take a look at this tick count and open it up, we notice that the counter units we've selected is ticks, and then the size of the internal counter is 32-bit. Okay. And this code here at the bottom, we're just trying to make sure that it's not the first iteration. So over here, if the iteration is not equal to 0, so it's not the very first iteration of the while loop, then we're going to go to the true case and we're going to update what the loop period is. Okay. If we go to false, so if this is the very first iteration of the while loop, then we have nothing to compare to, so we're just not going to do anything. Okay. But on all subsequent iterations, we're going to go ahead and update the loop period indicator. Okay, so let's go to our front panel. And in this case, we've already compiled it. So this is this VI when I hit run is actually going to be running on the FPGA. So let me hit run. So now it's reading the current thermocouple signal. It's showing what the maximum value was reached, and it's also showing our current minimum reached. Okay, and in addition to that, we're seeing what the loop period is. Okay, so let me hit stop. Okay, so let's take a look at this loop period. So the loop period looks like 275556 ticks. Okay, so to get that in back into units of seconds, we're gonna have to do some conversion on that. Okay, so we see that the loop period is going to be ticks, and the way that we convert that into seconds is we're going to do a conversion based on the FPGA clock rate. So the default FPGA clock is going to be 40 megahertz. So to convert it from ticks based on that clock, a 40 megahertz clock is going to be 40 million ticks per second. Okay, so I'm going to take this ticks over here and divide it by 40 million. So notice that over here we've got a sample calculation. Let me go ahead and do the calculation with our current numbers. So if we take our current loop period in ticks, we've got 2755536, and we're going to divide that by 40 million. So 40 million. And if I hit equals, that gives us 0.06888 seconds. In other words, it's about 69 milliseconds. Okay, so that loop period took about 69 milliseconds. If we look at the block diagram, the thing that's going to take the most time on this particular loop is actually this analog input. So analog input is typically going to be a slow function. So if we look at the actual specifications for this module, we would see that for 9211, which is what we're using, the conversion time is about 70 milliseconds per channel. Okay, so our benchmark of about 69 milliseconds is pretty accurate. Okay, now let's take a look at the discussion questions. So in this exercise, if we configured a tick count express VI to use counter units of microseconds or milliseconds instead of ticks, would the benchmarking results in this exercise still be reasonable? What do you think? So if we were thinking about this particular exercise, the loop rate was about 69 milliseconds, right? So if we were using counter units of microseconds or milliseconds, that would still be accurate enough resolution to be reasonable. So if we use milliseconds, for example, we still would have gotten a benchmark of about 69 milliseconds. However, let's say the code that we're trying to benchmark actually executes within nanoseconds. What counter unit should you use? Should you use ticks, microseconds, or milliseconds? So if you want to measure something within nanoseconds, you're going to have to use ticks, because that's going to be the only unit that has the resolution to actually measure in nanoseconds.